Geology has been a science for little more than a century. For most of that time, geologists have mapped and studied the Earth's surface, trying to discover how it was formed and what forces within the Earth caused it to change with time. Most of the work was simply tedious mapping and study of the rocks in small areas. But through the years, geologists also began to look for principles that might explain the larger patterns and processes that have shaped the Earth. Before scientists tackled the problem, there was a popular belief that the Earth had been formed by a series of giant cataclysmic events. But when geologists began studying the rocks, they found overwhelming evidence for a principle they came to call uniformitarianism. Uniformitarianism is a big word, but it simply means that the present is the key to the past. It assumes that the same forces we can see at work, raising mountains and carving valleys today, have been at work for millions and millions of years, reshaping and molding the surface of our planet. As they worked, geologists found they needed large concepts called theories to help explain the patterns they were finding in the rocks. One such theory was developed by James Hall about 30 years before the Civil War. Hall was mapping in the northern Appalachians. He found that the mountains were made of broken and bent layers of sandstone, shale, and limestone. But he was puzzled by the evidence because it indicated that the rocks had been laid down as flat-lying beds underwater in a shallow sea. When he measured the rocks, Hall found that there were more than 12,000 meters of sedimentary rock in the Appalachians. Immediately he asked himself, how could 12,000 meters of sedimentary rock be formed in such a way that each layer was deposited in a shallow sea? Hall proposed that a long trough-like basin had formed running north and south. His study of the Appalachian rocks indicated that mud and sand had been carried into the basin by streams coming from mountains to the east and to the west. As the sediment accumulated in the basin, the land sank under the increasing weight. So here was the answer to Hall's question of how 12,000 meters of sediment could form in a sea only 100 meters deep. Hall's idea is called the geosynclinal theory, based on his name for the trough-like basin, which he called a geosyncline. But there were still many questions that Hall couldn't answer. The streams flowing into the trough from the west could have come from land, but to the east there was only the Atlantic Ocean. Where could the streams have come from? Hall didn't know, but he did know that the sand and mud had to come from somewhere. Hall's theory also couldn't explain the way in which the land in the trough sank. 50 years later, another American named Dutton suggested an answer to the sinking problem. Using new evidence gathered in India by British geologists, Dutton suggested that the outer layers of the Earth formed a relatively light but rigid crust. The crust floated on denser inner layers of rock called the mantle, which in turn surrounded the core of the Earth. The mantle rock behaved like a plastic, moving slowly in response to changes in the crust above. This model behaves in much the same way as the crust and the mantle. The wooden blocks represent the crust and are floating in oil, which represents the mantle. If we add a large mass of rock, like a mountain range, to a section of the crust, it will sink into the mantle. In the same manner, if erosion removes rock from a mountain range and deposits it in an ocean basin, the crust beneath the ocean basin will sink under the added weight, while the crust beneath the mountain range will rise. This explanation is called isostasy and refers to the floating of less dense crustal rocks on the more dense rocks of the mantle. Yet neither isostasy nor the geosynclinal theory can explain the fantastic energy required to fold and bend and thrust these sediments up, forming mountain ranges around the world. Yet for many years, this was the best explanation that fit the evidence. It wasn't until World War II that scientists got the tools they needed to begin to investigate the planet. Naval vessels using sonar began mapping the ocean floor, and what we had thought was barren, featureless plains turned out to be more rugged than any continent. This map, produced by the National Geographic Society, shows mountains higher than Everest rising from the ocean floor, and canyons deeper than the Grand Canyon cutting across the bottom. Near the middle of the Atlantic, they discovered a long chain of mountains which they named the Mid-Atlantic Ridge. Down the middle is a great rift valley which splits the ridge in half. Scientists began studying the ridge by towing a magnetometer over the range. They knew that as molten rocks cooled, the mineral grains were frozen in the direction of the Earth's magnetic field. The rocks of the Mid-Atlantic Ridge all showed magnetized bands, but in some bands, the north and south poles were reversed. Geologists were fascinated by the apparent reversal of the Earth's magnetic field, but they also noted that the pattern of the bands was the same in both directions as one moved away from the center of the Mid-Atlantic Ridge. The question was what the repeating pattern meant. If it meant that the seafloor was spreading and new rock was moving up at the center, then the rocks at the center of the ridge should be younger than the rocks to the east or the rocks to the west. A scientist named Hess proposed that the seafloor was indeed spreading outward and that new rock was moving up at the center from the mantle below. The new wealth of information was bringing a new picture of the Earth, one that called for the revival of an old, almost forgotten theory. 30 years before World War II, a German geologist, Alfred Wegener, had proposed that the continents were moving. Wegener was fascinated by the fact that the shorelines of Africa and South America and Europe and North America seemed to fit together. But Wegener was primarily a glaciologist, and he was puzzled by unexplained glaciation in India, the African Sahara, Australia, and Antarctica. He found that when he fitted the continents together in a particular way, the unexplained glaciers all moved out from a common center. So Wegener proposed that the continents had all once been part of a large landmass. He called that landmass Pangaea, meaning all lands. And he also suggested that about 200 million years ago, the landmass broke up, allowing the continents to drift to their present locations. Until the discovery of magnetic bands, his proposal had been given little support. But now, scientists began to give it more attention. To find out if the crust was spreading, a new kind of research vessel was sent to sea. The Glomar Challenger was the first ship to carry a drilling rig designed to drill and recover cores from the bottom of the deep ocean. The work began in 1969. For 3 years, the evidence came in slowly, as hundreds of holes were drilled across the mid-Atlantic ridge and other deep ocean ridges around the world.
Okay, number 10.
Number
150 meters.
The cores were studied and the rocks were analyzed and dated. Cores from either side of the mid-Atlantic ridge backed up the magnetic evidence. Rocks near the center of the ridge were very young, while rocks further away on either side were much older. New rock was indeed forming along the Rift Valley and moving outward in both directions. The crust was spreading, not just along the mid-Atlantic ridge, but along mid-ocean ridges all around the world, and other studies began to back that up. Studies of heat flow through the crust from the mantle showed higher than average heat flow along the deep ocean ridges and less than average heat flow along the deep ocean trenches. Geologists studying the heat flow found hot spots which corresponded to volcanic centers like the Ascension Islands in the South Atlantic. They also found other interesting features on the deep ocean floor. Here in the Pacific, chains of ancient volcanic cones were found stretching away from today's center of activity in the Hawaiian Islands. Here was more evidence that the crust was moving, this time over a hot spot in the mantle. Wegener's idea of matching the continents was tried again, this time using computers, and the fit was amazingly good. Here, the edges of the continental shelves, shown in blue, can be seen to match with an error of less than 1%. Areas where they overlap are shown in black, while those where they don't quite match are shown in white. Of course, the next question was, did the rocks of the continents also match? Radioactive dating, fossil correlation, and many other techniques were used in an effort to determine if the rocks on the different continents were the same age and type. The rock units shown here in different colors were found to match. Those in northern Africa and Europe matched those in the United States and Canada. The rock units in India, the Antarctic, and southern Africa also matched. But the best match of all came between the rocks of South America and western Africa. Now we know that the continents can be matched up, not only in terms of shape, but in terms of rock units which cross from one continent to another. We also know that the continents came apart and that new crust is forming where they separated. But we live on a globe, so if the crust is separating in one place, it must be colliding in another. The next thing we need to find out is what happens where two sections of crust meet. The answer was supplied by seismologists studying the behavior of earthquake shocks called seismic waves. They confirmed that the crust is thin and plate-like, and that the mantle rock underneath the crust behaves like a plastic, capable of flowing very slowly. The seismologists had long known that belts of earthquakes stretched around the Pacific Ocean, down the mid-Atlantic ridge, across the Himalayas, and through the Mediterranean. They also knew that active volcanoes were associated with the belts of earthquakes. In fact, there were so many volcanoes along the belt that stretched around the Pacific that it had come to be known as the Ring of Fire. With the new information, they discovered that the belts of earthquakes and volcanoes marked the boundaries where crustal plates were separating or colliding. If you look closely, you will see that the trenches in the ocean floors are related to the earthquake and volcanic belts, and they also match chains of young rugged mountains around the world, like the Japan Trench next to the famous mountain volcanoes of Japan. Or here on the west coast of South America, where the Peru-Chile Trench lies next to the young, rugged, and volcanic mountains of the Andes. Geologists realized that the combination of ocean trench and young active mountains marked the collision of two crustal plates. Here, the Pacific Ocean plate is colliding with the South American plate, and as the ocean plate slowly moves downward, earthquakes mark the movement, and as the center of quakes get deeper and deeper, the plate moves eastward down under the continent. The descending basalt of the ocean floor, carrying sediment and some ocean water, gets hotter and hotter until melting creates the magma of the volcanoes above. When plates collide under the ocean, the resulting volcanoes form islands like those that form the islands of Japan or the Aleutians. But not all plates collide head-on. In some places, plate edges are sliding against one another. One such sliding contact occurs along the coast of California. The famous San Andreas Fault is the junction between the Pacific Plate and the North American Plate. Earthquakes are very common along this break in the crust, and each shock marks some movement of either the North American or the Pacific side. So, as you can see, the pieces of the puzzle fit together to form a picture. Belts of earthquakes and volcanoes, continents which match in terms of shape as well as rock units, matching glaciers and fossil life forms, and bands of magnetized rock. Here then was the answer to James Hall's problem. He wanted to know where the mountains had gone, that had supplied the sand and mud to the developing geosyncline. What was left of the mountains went east with Africa, while the Appalachians went west. But most important of all, the drifting crustal plates provide a force that can raise mountains. Here then was enough evidence for Robert Dietz and John Holden to use a computer in an effort to trace the paths that had been followed by the drifting crustal plates. The story began more than 200 million years ago, near the end of a time geologists call the Paleozoic era. At that time, all of today's continents were assembled into one supercontinent called Pangaea. Then, some as yet unknown force began splitting the crustal plates apart, creating two large continents. We call the northern one Laurasia and the southern one Gondwana. By the end of Triassic time, about 180 million years ago, the Atlantic Ocean had begun to develop along what is now the Mid-Atlantic Ridge, as Gondwana moved east and the North American plate moved west. As time passed, Gondwana began to break apart. Australia and Antarctica moved southward. India began drifting to the northeast, and South America separated from Africa, moving toward the west, slowly opening today's South Atlantic Ocean and raising the Andes Mountains. About 50 million years ago, Australia separated from the Antarctic. And 20 million years ago, India collided with Asia, causing a crash that is still raising the Himalayas. Today, the North and South American plates are moving westward about 1 centimeter every year, while Africa is splitting along a large rift zone through Lake Victoria. If the continental plates continue to drift for another 50 million years, Australia will collide with New Guinea, and San Francisco will be part of Alaska, while North and South America will continue drifting westward toward the setting sun. The next question most geologists ask is what causes plates to drift? Some research suggests that convection in the Earth's mantle caused by heat from the Earth's interior might be dragging the plates along, but the rotation of the Earth and the pull of the Moon might also be forces to consider. The theory of moving plates seems to explain the theories of mountain building. While geologists have begun to consider this theory only recently, they've long studied bent and broken rocks like these, which make up mountain ranges around the world. And they will continue to ask questions like, what happened before Pangaea? Was it too made of plates? Were there supercontinents before Pangaea? More questions than answers, but at least we know that the rocks of the Earth are not static, for even the continents are moving.